All right, so we are continuing with our coverage of the Chapter 8 problem solving session into question number 4. And again, if you haven't already done so, you can access the entire worksheet on Canvas under Files. You can print it out, you can try these problems on your own, and then use this video to go through the solutions and make sure that you're on the right track, or use this video if you get hung up on one of the problems. So let's take a look at to provide the major organic product of the following reactions, showing the absolute configuration of the reaction products. So we're going to start with cyclohexene, 6-carbon chain, 6-carbon ring rather, since we got the cyclo word in there, carbon-carbon double bond, reacting with chlorine. And in order to make sure that I'm on the right track for getting to the right product of this, I'm going to sketch out at least some of the steps of the mechanism here. So we have our alkene reacting with chlorine, Cl2. So double bond comes in, forms a covalent bond to the chlorine. That forces the chlorine-chlorine bond to break, like so. And that's going to give us a carbocation in one of these carbons, and chlorine here. And we would also be generating, as a result of this step, chloride anion as well, because we broke that bond between the two chlorine atoms right here. So the special thing about this situation where we have a carbocation and a chlorine that are vicinal to one another, meaning attached at adjacent carbon atoms, so adjacent carbon atoms have a positive charge, and a chlorine or other atom with a lone pair of electrons, is that we can have a special kind of resonance co-on here to form a 3-membered ring that bridges across here and acts to stabilize the molecule. So our second resonance structure here, that's a very important resonance structure, would have our chlorine atom here as part of a 3-membered ring, and then 2 sets of lone pair electrons and a positive formal charge there. So now that we have that bridged structure in place as one of our major resonance structures, keep in mind that there will be no carbocation rearrangements go on in any cases where we're reacting an alkene with chlorine, because this resonance is a more strong stabilizing factor. It's going to stabilize the molecule, and it eliminates the need for there to be a carbocation rearrangement to stabilize a secondary carbocation into a tertiary carbocation. So whenever there's resonance to stabilize a molecule, do not do a carbocation rearrangement. The resonance here is a stronger stabilizing force. So we have our resonance structures that we've drawn here. And then what's going to happen is that the chloride anion that we generated as a result of the first step of the mechanism is going to come in. It's going to attack one of the two carbons there of the carbon-carbon, one of the two carbons there of the bridge, and force the carbon-chlorine bond to break right there so we don't go over the octets. And that's going to lead us to our product of this, where we have our two chlorine atoms that will be vicinal to one another. Vicinal meaning that they are attached to adjacent carbon atoms. Vicinal chlorine atoms there. And the question it specifies here, not just to show the product, but to also show the absolute configuration of it. In other words, show what the configuration is of this molecule in terms of the wedges and dashes. So we need to think about what would be the case there. And in this particular problem, the key to determining the absolute configuration is to think about the restraints that are put in place by the fact that we have this 6-membered ring linked to our 3-membered ring here, and how that's going to impact what face of the molecule that green chloride anion comes in from. And what is going to have to happen here in order for the reaction to not face a huge amount of steric hindrance is that this chloride anion has to attack the face opposite where the first chlorine atom is and where that bond is breaking away. So the second chlorine is going to attack the face opposite the first chlorine. And so, in other words, if the first chlorine atom is oriented toward the back side of the molecule here with dashes, that means that the second chlorine would have to be coming in from the front side and would end up showing up as a wedge. So in other words, the outcome of this is that the two chlorine groups have to be added trans to one another. It is an example of anti-addition. So the stereoselectivity here is anti, and you could think of anti generally referring to trans, meaning that the two chlorine atoms are going to be on opposite faces of the molecule. Now keep in mind that there are two different trans stereoisomers that we can draw here. We can draw that first one, and we could also draw the enantiomer of that, like so. So our two major organic products, including showing the absolute configuration of those, would be these two molecules. They both correspond to having two chlorine atoms that have added across the carbon-carbon double bond, and the reaction is stereoselective in that it prefers the anti-product, the product where the two chlorine atoms are going to be on opposite faces of the molecule, because the first chlorine atom comes in and attacks from the face opposite where the other one is leaving, and that's to minimize the steric hindrance of this process here. So this step that I'm circling is the key to assessing that the stereoselectivity is going to be anti. The chlorine that's coming in and attacking and acting as a nucleophile has to attack from the face opposite, where that bond in red right here is breaking away. So let's do this same sort of process here for the next question. In part B, we just mix it up a little bit by changing our organic starting material and changing exactly what we're reacting with, but we're going to go through the same sort of process here. So 1,2-dimethyl cyclohexene, put our methyl groups in there, reacting with chlorine and reacting with water. Our first step of the mechanism is going to be completely analogous to what we did up top here. That is where we will be bringing in our chlorine. The bond between the two chlorine atoms is relatively weak. I'm pretty happy to break there. So it's going to get attacked by the alkene, comes in, forms a covalent bond to the chlorine, forces the bond between the two chlorine atoms to break, and that's going to give us a new chlorine atom on one of those two carbons, positive formal charge on the other, and then we'll be in that resonance situation again like we were up top, where the chlorine lone pair electrons are going to come over and form that three-membered ring that links the six-membered ring to our three-membered ring. Like so, positive formal charge goes onto the chlorine, and don't forget those methyl groups are going to remain there as well. So then at this point, similar to above, we need a nucleophile to come in, and here's where the plot twist happens. So in this reaction, rather than just having chlorine available, which was what we had available up top here in part A, instead in part B we have chlorine and water available. And so what's going to happen here is that the water is going to act as the nucleophile, the preferred nucleophile here, to attack. So water comes in, H2O. It is going to attack here as the chlorine leaving group breaks away, and that's going to lead us to our next intermediate here. We have a chlorine, and now the water has formed a bond there. And then at this point, we would lose a proton, so I'm going to put minus H plus there to indicate deprotonation. Similar to when you were doing hydration reactions and you lost a proton from water that had bonded to our organic molecule, to give this structure, and this would be referred to as a vicinal halohydrin. Vicinal because the two groups are on adjacent carbons, halo because of the halogen, hydrogen because of the water. And to assess the stereochemistry of this, we keep in mind the same principles that we did up top, where up top, the chlorine anion nucleophile had to attack from a face opposite where the chlorine leaving group was breaking away. The same is going to be true down below here, that if our chlorine atoms are linked there via two dashes, that means that the water has to come in and attack from the opposite face. So the water would have to come in and attack as a wedge, making that chlorine a dash. And then to fill in the full tetrahedron, I'm just going to put wedges and dashes on my methyl groups there as well. Additionally, Much like up top, you need to draw the enantiomer. There will be two of these trans enantiomers. So make sure you get both of those in. The reaction is stereoselective because we're skipping the cis molecules where the hydroxy group and the chlorine are cis to one another. We're only doing the ones where it's trans. And so we have these two as our final major organic products of this reaction.